Next up, the loop law. The loop law says that if I measure all the changes in voltage around some loop of, any loop of a circuit, okay, I'm going to take an easy one here, the change in all the voltages must add up to zero. This just goes back to the whole idea of potential. Remember, potential between point A and point B can only be dependent on the points, not the path I take to get from one point to another. We've encountered this a bunch of times already this semester. I've pitched you homework problems, quiz questions, things like that on more than one occasion. So this shouldn't be surprising. In this case, we're just saying if I go all the way around a loop and A and B are the same point, well, there should be no potential difference. Okay? So in this case, if I've got some voltage V and some resistance R in my battery and my resistor respectively, then if I go around, I get a plus V going this way. Okay? Keep going, keep going, keep going, keep going. Oh, hit a resistor. I drop by the current times R. Keep going, keep going, keep going, keep going, back where I started. So that's all equal to zero. What this implies is, in this case, the voltage across the resistor is IR. Well, you already knew that in this case. It was a pretty simple application. Okay. We can make this more complicated, though. We are going to make it more complicated. A more general way of writing this, by the way, is the sum of all the changes in voltage around a loop is equal to zero. Okay? Now, in some circuits, we're going to have things like this. Resistor, and maybe a resistor here, and maybe a battery here. Just putting lots of old resistors in, R1, maybe R2, R3, a V1, a V2. Well, what are we going to do in this case? Well, what we're going to do is start at any point I choose, go up and over, V1. I'm going to go down this one, call this I1, just by convention. And back minus I1 R1 is equal to 0. Well, I got other loops I can do, though, right? I can do a loop around here. I'm going to start here maybe and just do a loop this way. Okay? I'm going to call that I2 and I3, just guessing. So starting, I got V2 minus I3 R3. Okay. And then going up, nothing interesting happens over there. And then I2 R2 equals 0. Okay. There's one cool thing I can also do with this, which is to realize that because there's no place for the current to go between these 2 points, I3 and I2 are the same. But at this point now, I've got 2 equations. Now you might notice there's an extra big loop on the outside. Okay, and there is, but it turns out if I add these 2 equations together, I actually would get that outer loop. We'll talk more about that in a subsequent class when we talk about multi-loop circuits and practice on multi-loop circuits. Okay? But with this, along with the junction rule, I can analyze any circuit of this type. Okay? I can find circuits that these will not be as useful with, but these are always a starting point for every single circuit. And it will get you what you want to know, because at this point, if I know the voltages and I know the resistances, I can find actually all the currents. Okay? If I know a current someplace, I can find maybe some of the voltages, some of the resistors, some of those kinds of things in my circuit. That's what it means to analyze a circuit. So at this point, we're going to be doing a lot of solving of systems. If you don't remember how to solve systems, linear systems of equations from algebra class, go back and review it now. Trust me, you're going to be glad that you did. All right. I will see everybody in class. I hope this has been a help. Bye.